Another thing for your future that's worth knowing is how to interpret the meaning of the curl. On Wednesday, we talked about the meaning of the divergence related to fluid flow based on the divergence theorem. You got a surface, pretend it's a sphere, a closed surface, maybe a sphere. You got a vector field, maybe pointing about like this across the surface. You're wondering what's the flux of the vector field with respect to outward pointing normal vectors, say, along that surface that's maybe a sphere. The flux integral is a double integral over the surface. The divergence theorem says it's the triple integral of the divergence over the entire solid sphere, including the inside. If you get a positive triple integral for the divergence, it's a positive divergence. That means fluid is flowing out of the surface faster than it's flowing in. You get a negative divergence, that means fluid's flowing in faster than it's flowing out. You get a zero divergence, it's flowing in and out at the same rate, which you would think would be more realistic. But mathematically, anything can happen. Likewise, we can interpret the curl in terms of fluid flow, though it's easiest to think about with 2 dimensions. And Green's theorem, here I have a different book, and 2 things to say about Green's theorem and the curl. This is the statement of Green's theorem. Remember, Green's theorem, Stokes' theorem essentially just generalized Green's theorems to higher dimensions. Green's theorem is a little easier to draw. You can just make drawings in 2 dimensions like this. This particular domain is rectangular, and it's got a boundary that's got 4 lines to it. It is oriented counterclockwise. And remember, with Green's theorem, you do need the boundary to be oriented counterclockwise in the plane. It's saying that the circulation of the vector field around the boundary is equal to the double integral of this curl here. Because it's a 2-dimensional vector field, this curl is a scalar. How could it be a scalar? Aren't curls vectors? It's the 3rd component of the vector. Come back here. It's essentially the 3rd component that we focus on for with the scalar curl. It's the curl of the vector field m comma n. It's the 3rd component. Our book wrote an nx minus my there. So it's the double integral of the curl. And just like we do with the divergence theorem, I think on Monday, to think about this intuitively, imagine doing this over a small region, like a small rectangle like this. If this rectangle is really small, the scalar curl is not going to vary much in value over the rectangle. It'll be effectively constant. You can approximate the double integral as a product of the approximately constant scalar curl at a point times the area of the rectangle. With the divergence theorem, we did the approximately constant value of the divergence times the volume of this small region. And because of that, and because it equaled the flux over the surface, we said the divergence could be interpreted as flux per unit volume. Likewise, the curl, because of this equation, can be thought of as circulation per unit area, because that line integral represents circulation. How much is the vector field flowing with the curve? Circulation per unit area if you divide both sides by the area. And that, through a bunch of explanation, which I'm not going to go into the details of, ultimately says if you put a little paddle wheel in a 2-dimensional vector field representing a thin sheet of fluid, effectively a 2-dimensional fluid, free to rotate. This is a little easier to imagine because you could kind of imagine like you got 2 I don't know, plates of glass that are really close together, and you've got a really thin sheet of fluid between them. And you put a little paddle wheel inside there, and you've like attached it to the glass so it doesn't move. Okay? So you could imagine trying to actually do this. And you attach little paddle wheels to this thing. It could start rotating. It will start rotating, in fact, if the curl is not 0. If the curl is positive, it'll rotate counterclockwise. If it's negative at the point, it'll rotate clockwise. And in fact, they claim here that the angular velocity of the paddle wheel, it would be in radians per second, say, is 1/2 the value of the curl. Can that be understood beyond just taking it as a given in the book there? Yeah, I mean, you could try to set up an experiment and see if it works. You could try example vector fields and see if it works. Oh, for example, this vector field is kind of a good example to think about. So it's a two-dimensional vector field. What does the vector field look like? There we go. Oh, look at that vector field. It's rotating. Does that mean little paddle wheels rotate? You would think so. But they're not flowing around. They're not rotating around the origin like this. They're spinning where you got them fixed. Now, certainly at the origin, in the middle of the picture, you would think it would rotate because the flow is around the origin. And in fact, the scalar curl here is the derivative of the first component with respect to the second variable. No, the second component with respect to the first variable. The second component is x here. Maybe I should type it in as the vector field itself. No, that's not going to work. Okay, let's use an m and an n. M of xy here. The first component is negative y. N of xy, can't use a capital N, is the second component, that's x. The derivative of the second component n with respect to the first variable minus the derivative of the first component m with respect to the second variable, that is the curl, and it's positive, constant. The scalar curl here doesn't depend on where you are, it's always true. So if you put a little paddle wheel at the origin, certainly, it makes intuitive sense that it would rotate with angular velocity, half of this, 1 radian per second, I guess, counterclockwise because it's positive. But it's also true if you put it elsewhere besides the origin, it would still rotate with the same angular velocity. That's less clear. Is there any way we could understand why that happens, even if we put it somewhere else besides the origin? What if we put it at the point 1, 1? What does the vector field look like close to the point 1, 1? The vectors should be mostly pointing in the same direction, so how can the paddle wheel rotate? Well, remember, more orangish yellowish vectors are really longer vectors than the blue purplish ones. So even though these vectors near the point 1, 1 are basically all pointing in the same direction, the ones that are further away from the origin are longer than the ones that are closer to the origin, meaning the fluid is moving faster further from the origin than it is closer, meaning the water molecules have more velocity, more energy, more momentum. They are imparting a counterclockwise rotation of that little paddle wheel near the point 1, 1. And in fact, yes, no matter where you are, the scalar curl here for this example is the constant 2. And so, yes, if you could set this up somehow in an experiment, no matter where you put the paddle wheel, it would rotate counterclockwise with an angular velocity 1/2 of that, 1 radian per second. We're ignoring things like friction when we say those things. I mean, I suppose when you stick the paddle wheel in there, it wouldn't start rotating with that angular velocity right away because it has to accelerate, so to speak. But if you kept friction somehow to a minimum, eventually it sort of gets to the point where it's rotating at that angular velocity. This applies no matter where you are. It's not just at the origin.